So let's start with the problem we just talked about. Oops, I don't want one of those. We'll have a disk down here, a disk down here, and a ring. And we roll them both towards this ramp. Now, if we roll them so that they have the same velocity, you guys clearly indicated that the disk would have less energy than the hoop. I don't think that's unreasonable. Rotational kinetic energy is 1/2 I omega squared. Translational kinetic energy, as you know, is 1/2 mv squared. When they are rolling at the same speed, they have the same translational kinetic energy. Their linear velocity is the same, and they have the same mass. But they don't have the same angular velocity. The moment of inertia of the disk is half that of the ring, so it would have half as much kinetic energy for the same rotational speed. Ultimately, that means that the disk has 3/4 the amount of energy of the ring, not half, because they still have the same amount of translational kinetic energy. I'm not sure if we got 3/4, but it's not half, it's more than half. So questions come up like, which one will roll up higher along the ramp? That one should be pretty easy because we know which one has more total energy. So assuming they roll up the ramp, then the one with more energy should go up higher along the ramp. Now, the other side of that is, that assumes it rolls up the ramp. Which one rolls up higher if the ramp is frictionless? Think it through all the way. I hate to people put their hands up right away because they just kind of hear themselves talk. I'm not calling on anybody like that, but think it through all the way. Now, do you have an answer that you can articulate? Kieran?
It just seems like it should be going at a faster velocity when it reaches the base of the ramp. Therefore,
No, they both have the same velocity.
oh, so they go the same distance.
Luke?
They go the same height because of that friction and rotation kinetic energy. So one thing that matters is translation kinetic energy.
Max?
So, similar answer.
Speak up too so they can hear you at home too.
I have a similar answer to Luke, but it's because at the top, they're both still going to be rolling at the same rate as they were rolling starting going up the ramp in terms of angular velocity. So they're going to have the same angular velocity top and bottom. That won't change.
All right, let me articulate what Max said so you can all hear it. Max said that if it's frictionless, then when they make it to the highest point on the ramp, they will still be spinning, which is true. If you push a block up a ramp, it will eventually stop because gravity is going to slow it down, which is a component of the unbalanced force down the ramp. Same is going to be true for the disc and the ring. But when they make it to that point up on the top, their highest point achieved, they're not going to be stopped. They're going to have no translational velocity, but they will still have rotational velocity. There has been no unbalanced torque, and therefore there has been nothing to stop the rotational motion. So they will go up to the same height along the ramp, but the ring still has more energy. It had more energy at the bottom, it's going to have more energy at the top. So its rotational kinetic energy still exceeds the rotational kinetic energy of the disk. You have a minute and like 10 seconds to answer each multiple choice question on the AP exam. Do you understand that all of these answers differ by which word I choose to say at the beginning of the problem? Disk and a ring have the same velocity. Disk and a ring have the same kinetic energy. Disk and a ring have the same, there's a lot of things there. frictionless versus friction filled. What's interesting though, and I want you to consider, if we add friction on the ramp, so it's not frictionless, and I ask you which one goes the higher amount, and you say it's the ring because it has more energy, everything about that statement is right. But why? Why does the ring climb up higher on the ramp? If you can't use the word energy in your explanation, I want you to think about what it would mean for it to climb up higher along the ramp. It would have to be pushed higher up the ramp somehow. We have not talked about rolling and what rolling actually is. Not that I don't think you know what rolling is. I think all of you could state that, rolling is when something rolls across the ground. But could you be more specific? What does rolling actually mean? All right, Luke. There is one single statement that tells you what rolling is. When that is true, the object is rolling. When the angular velocity is matched with the linear velocity, the object is rolling. This brings up an implication that there will be a single point of contact that is in static equilibrium instantaneously with the ground, meaning the point in contact with the ground does not slide with respect to the ground. This is rolling. When this condition is true, we are rolling. That seems like not very much, but understand, rolling is not going to be easy. When we get to talking about rolling, trust me when I say it's not going to be easy. And there's a lot of reasons to kind of dwell on it, and I don't want to right now because we need to cover some more basic ideas first. But the one thing that I do want you to think about is, let's say that the disc and the ring are on the ramp and the ramp has friction and they are rolling this direction up the ramp, slowing down. What direction do you think the frictional force is on them as they slow down on their way up the ramp? It's going to be an all skate here. You're either going to point upwards for up the ramp or downwards for down the ramp. So on the count of three, this involves everybody, but there's only one camera on for the people at home because got a lot of people checked out. So you're either pointing up the ramp or down the ramp. What direction is the frictional force? It's either up the ramp this way or down the ramp this way. 1, 2, 3. Funny, we are nice and evenly split. So just so you guys know, it's a pretty even split. This is not as hard as you think, but it is hard. I mean, your brains are probably hurting a little bit about what you should put here. What direction is it spinning as it goes up the ramp? Clockwise or counterclockwise based on what I have drawn right now? So it is spinning this way, clockwise. If I want to stop its spin and I can only push on the edge, what direction would I have to push on the edge to stop the spin? So as it rolls up the ramp, the frictional force acts up. What's crazy is that means that mg sine theta must be greater than the frictional force. It would have to be because it's slowing down. The net force still works, but the two forces go in the opposite direction. What's really going to blow your mind about this is you're going to want friction to be equal to mu times the normal force, and it's not going to be. We are never near the maximum. When you're at the max, that means you're about to slide. Generally, static friction is very small for objects that roll. very small. So this is a little bit more in our future. It's not our present. I think we should do some problems that are more in our present. So let's start with the present. Yesterday, we talked about moment of inertia. So right now, though, I want to talk about angular dynamics. Now that we know about moment of inertia, I see that we have 4 things that we have to kind of deal with now that our systems have extension and we can deal with acceleration due to their inertia. The first is we are going to have to deal with moment of inertia. And what I mean by that is you're going to have to be able to do the math. I'm going to put that off a little bit because although I think there's something that you should do for me, and I didn't assign it, I didn't assign a meter stick problem to you guys yesterday, did I? I'm going to assign a meter stick problem to you right now. And it's to help prepare us for moment of inertia. We're going to do a little bit of this each day. And today is no different. So in a few minutes, Mr. Shelton, in a few minutes, we're going to talk about the meter stick problem. I'll put that over there because we're going to need the meter stick. Point number 2, we need to deal with Newton's laws. They're now going to have to change. We're going to have to deal with Newton's laws for both force and torque. We're going to have to go and make another run through energy problems. And of course, a new definition for the work energy theorem, because work can be done by a torque. And lastly, we'll finally deal with angular momentum. I'd like to tell you that these are all things that are similar to what we've already learned. You're just, doing it for rotational motion, but they're not. It's in addition to translational motion. Objects can do both. And because of that, we need to be cognizant that an object's energy isn't just its translational energy. Throw a frisbee, the object has more than one kind of energy now. Gravitational potential because it's above the ground, translational kinetic energy, and rotational kinetic energy, and they're not linked together in any meaningful way. We will see problems that link them together, but an object can have both angular momentum and linear momentum. They're not the same. And because they're not the same, things behave differently when they have each. So we need to redress each of these, and it's going to take a couple weeks for each. I think this puts us through rotational motion probably till first week of March. I'm going to kind of put the heavier math pieces off to do a little bit at a time. So I'll be working them in a little at a time. And today is going to be the first one. I want to talk about how we take an object like a meter stick and figure out what its moment of inertia is. But I'm going to go old school, like calculus on you guys, because I don't know, just to be mean, I think. Because if I spring this on you, I'm going to use words that your math teacher doesn't use, and you're going to be all mad at me and stuff, and I don't want to deal with that. So here's what I want you to do instead. I want you to calculate the moment of inertia of a meter stick about its end using the basic calculation, the point mass calculation. And what I mean by that is I want you to break the meter stick up into 10 pieces. Each piece is going to be 1/10 of a meter stick. Devon, how long is a meter stick?
3 feet.
Every time, huh? Every time. It's 100 centimeters, which means each one of these is 10 centimeters. And each one of them has a mass of 1/10 m. Right? 1/10 m. So what I'd like you to do is assume that for every 10 centimeters, there's a center of mass located at the middle of that portion of the meter stick. So there's a center of mass right here, 5 centimeters away from the end. That is 1/10 of the mass of the meter stick. And there's another one right here. How far away would that be from the end of the meter stick? Oh, good, good. Not everybody gets that the first time, but yes, it's 15 centimeters. And then so on and so forth. You will have 10 pieces of meter stick. I'd like you to calculate the moment of inertia of the meter stick about its end using the summation formula. Bring it to me tomorrow. I'm not going to do it, I'm not going to do it now. And some of you won't be able to pay attention to what we're going to do because you can't possibly be given a problem and then keep working it. But I don't care. I'm moving on. I want you to use this. Do everyone understand what I'm asking you to do? Okay. Put it in meters, please. And we already know the answer. A stick spun about its end has a moment of inertia of 1/3 ml squared. So this is a meter stick. This should be 0.33 m. It won't be. That's why I want you to try it. Okay, so put that aside for now. Do that tonight. You have no other homework for me, so I'm not asking much. But I want to talk about Newton's laws, and today we're going to take a visit to the Atwood machine. Is it? The Atwood machine was never designed to do the kind of work we did on it. Atwood machines are designed the way we're going to talk about them today. If you don't remember the Atwood machine, then I don't know where you've been in a cave or something. An Atwood machine, the way we tended to talk about it, was either a modified Atwood machine, or in this case, a full Atwood machine. But even then, we didn't do a full Atwood machine. We did Atwood machines that looked something like this, where there was probably an M1 and an M2, and this was massless. Seem familiar? Today, we're going to talk about true Atwood machines. And what I mean by that are Atwood machines where we have a massive pulley, something with inertia. So let's move this to the center. And for our first attempt, we're going to take off I'm going to try to take off one of the masses. Okay, so we have a one-sided Atwood machine, but our pulley has mass M, capital M. Our hanging object has mass lowercase m, and the pulley has radius capital R. We're going to treat the pulley as a disk. So its moment of inertia is known, 1/2 mr squared. As I said to you before, it's in your best interest to begin to memorize the moment of inertias for at least the 3 objects we talked about yesterday that are the basic options. So a disk, a hoop, and a rod about its center and its end. Since there's lots of room upstairs in those brains of yours, I would try and remember more than that. But let's at least get those. Atwood machines are excellent examples for us to use Newton's laws. That's what they're really about. They're just to help us kind of exemplify a few things about Newton's laws. They're really a way for us to get an idea about inertia and how inertia plays a role in determining the acceleration of a system. They're good practice for interconnected problems where more than one object is moving at once. They allow us to explore energy and they allow us to explore force. So these are going to be force problems for the time being. So to remind you about force, we are almost always either looking for a single force or an acceleration. That generally is what Newton's law problems are about. So in this case, we have an unbalanced force acting on the end of our pulley. Our pulley is going to experience an acceleration. A lot of people think that because this is just rotating and there's no friction, that it will accelerate at G, as if the cable were cut and it's just falling, but that's not true. We already saw it with the example we had at the beginning of last week. We saw that the thing that was spinning, which was just an Atwood machine, It would spin slower if we increase the moment of inertia. In fact, it spun very slow, if you'll remember. So we know that there's rotational inertia. That rotational inertia is just like trying to lift up another box. What we want to see is how that plays a role in these problems. The start of these problems is the same as what we've already had before. We start these problems like any Newton's law problem. I believe the forces are going to be unbalanced, and therefore the unbalanced force will equal ma. If I'm feeling a little bit frisky, I might do the whole drawing of a free body diagram and everything. Not that I really feel like doing any of this, but it's just to kind of be diplomatic and to welcome you back into the world of doing Newton's law problems where you thought you might have been done forever. The difference in these problems is that our object is now connected to a pulley whose net force is 0. The net force on the pulley is 0. It does not change location. There is likely an upward force of, tension here, and a downward force of tension here, and they must sum to be equal to 0. There's probably also a force of gravity, mg. So we'll call this T up, and this is just the tension that's in the rope. Those have to sum to be 0, because the pulley doesn't change location. But 2 of these forces act at the center of mass. They can't rotate the object. The third force acts on the edge. It can cause rotation. That's an unbalanced torque. So just like what an unbalanced force would do, an unbalanced torque must cause an acceleration. How much acceleration? I don't think that's going to be a surprise. The amount of the acceleration depends on the inertia of the system. Newton's second law for torques. Net torque equals I alpha. So if we have an unbalanced torque, we will have an acceleration. The amount of our acceleration is dependent on the inertia of the system. I'm trying to be pretty slow here. Are there any questions? This is a relatively straightforward torque question, but I've clearly made downwards here positive, and I need to be consistent. So I'm making rotation in this direction positive as well. That would be a torque out of the board, which is consistent. That being said, let's take a moment and write out our torque. There are 3 parts to torque. The first is the length of the torque arm, which in this case is the radius of the pulley. The next piece in dealing with the torque is the size of the unbalanced force acting on the object. This acts at the edge of the pulley, so this is the string that causes the tension. And finally, we have to deal with the angle the string makes with the edge of the pulley. Anytime a string is acting on a pulley, this angle is going to be 90 degrees. It will always come off tangent. If you try to change that, it just unrolls or rolls around the pulley until it's, again, tangent. So whenever you have a pulley involved in your problem, you are always going to have the sine of 90 degrees. You always get a perfect torque. On the other hand, this is not equal to ma. This is equal to the moment of inertia. So our next thing is to drop in moment of inertia. We have a disk that's 1/2 mr squared. And all of that will help us determine what the acceleration of the system is. Just like every other force problem, a problem involving torque is just going to generate another piece of information. However, this new piece of information does introduce other variables. It's at this point where you have to determine whether there is a connection between the motion of the object on the left and the spinning of the wheel. Here's where you determine whether that string is actually rolling off of the pulley without slipping. That's an important phrase and one you should be listening for in these problems. In this problem, it's likely the string is spooled on that pulley. But you need to hear the phrase rolls without slipping or unspools without slipping. And make sure that you have that as a necessary part of your problem. Because what that does is it lets us know that there is a relationship between the linear acceleration and the angular acceleration. Do not take this for granted and don't assume it's always true. Be measured. We didn't have to do this with Newton's law problems before, but we did have to ask ourselves if the objects that were moving were connected in some way. If the motion of one was connected to the motion of the other. This is the connection you need to make. And it's the only way to solve these problems. Once you do this, you're going to have to make some substitution. And generally, we are almost always looking for the linear acceleration of the system. That's the most common thing to look for. And in this case, I'm going to substitute in for the angular acceleration. There's another reason to do this. And I get this in your notes if I were you. If done correctly, it's very likely the radius of our system will disappear, which is just weird to me. Still, every time I do it, that the radius has nothing to do with this problem. But that's what happens here. You see it? I get an R on this side, canceling with an R here. And then the only R that's left cancels with this R here. And I get tension equals 1/2 MA. I do think it's weird that the radius cancels out. And it does so all the time in these problems. When I think on it, maybe I can kind of grasp with why. I mean, the moment of inertia is based on R squared. That's the distribution of the mass. But the torque is also based on R. R gets bigger, it's more difficult to turn, but if R gets bigger, I'm applying more torque. But that only accounts for one of the R's. But the other R is related to the acceleration. If R is bigger, the linear acceleration is also bigger. Thus the other R. So it makes sense that it cancels out. It's still weird. But the result, when you cancel it out and you put these things together, comes right back to where we were first semester. Sub everything in so that now I'm dealing with the final part of the problem. And the first thing I hope you notice is we get back Newton's second law every time, but now for the system. Unbalanced force equals the inertia times the acceleration. The rotational inertia translated into a general inertia for the system. The entire mass of the pulley didn't matter, but half of its mass did. And because of that, it adds inertia to the system. In the same way that hanging another box would have had inertia on the system too, this system's inertia is based on how and what shape of pulley I have. Its mass isn't inconsequential here. And I hope you see that too. A heavier pulley is gonna invite more resistance to motion. But also, do you notice that we have a 1/2 here? Don't be complacent. That is the 1/2 from over here. So if I wanted to replace this with a solid sphere, it'd be 2/5. Replace it with a hoop or something where most of the mass is on the end, I get rid of it altogether and put a 1 in place. Meaning you're going to get a value here that represents the rotational portion of the moment of the inertia every single time. You should be expecting it. But I also am seeing that this represents the inertia as it pertains to the entire system with this unbalanced force. We get a linear inertia, even though the system is staying in place. I don't think this is too big a deal, but I put it here because I want you to make sure you understand that we will still get this portion here that is just a percentage of G. Not a surprise. This is a unitless factor. In the old days, it'd just be the mass of the other object there. Here, it's a part of the mass. Radius nowhere to be seen. However, if we wanted the angular acceleration, the radius would come into play. If I wanted the torque, the radius would come back into play. When anything else besides the linear information, the radius would make a showing. This is our first problem. Not so terrible. Any questions about it? I tried to be deliberate. See, I say it a lot. And I wanted to be careful to make sure that those of you who are new to this are, kind of being welcomed in a little bit. I don't think anybody did problems like this in their AP1 class last year. It was probably discussed in your AP1 class, maybe even demoed a little bit, but you generally weren't expected to go this far with AP1. It's on the curriculum though. But usually in AP1, they usually make it more of a, this is what's kind of happening. There's absolutely no reason you guys are not able to branch out right away and realize that we could redo this whole problem by asking how fast the box is going when it's dropped, say, a distance h. We just found the acceleration, so I know that you could use a motion problem, but do you also notice that that would mean this has gravitational potential energy, and that when it falls a distance h, it's going to have translational kinetic energy for this box and rotational kinetic energy for the pulley, that this is still the same kind of energy problem we've seen before, and you can be expected to do these as energy problems too. So although we're focused on Newton's second laws, I don't think it's too difficult for me to work in something here. Which brings me to what I would like you to do tonight for homework. I know you have to do the meter stick question, but I want to set you up for a lab too. A lab we will actually do, because everybody has access to the materials, or at least you used to. It's hard to tell if you have access to them now. You will need a roll of toilet paper. And I understand the difficulty in finding such a roll. But I was at the store and it seems like the crazy people are gone and we are back to having toilet paper in the store. I want you to consider this problem tonight. And I think you can do it, but I think you'll be challenged by it. If I hold the end of a piece of a roll of toilet paper and let it go, it's going to unroll. Some people think it will fall at G, but that can't be true. The toilet paper roll has inertia. And because of it, as it rolls, that inertia is going to try and resist the torque and therefore make it roll slower than falling at G. I would like to know the acceleration of the toilet paper as it unrolls. I'm going to give you a few pointers on where to begin. But the first thing I want to make sure you completely understand is that it will depend on the type of toilet paper. If you use luxuriously thick toilet paper, where the radius of the toilet paper changes drastically as it unrolls, you are probably going to get a different answer. So the cheap stuff works best here. But my wife and I have a deal in my house, and that is don't skimp on toilet paper. That's a good deal to make with your future person. Because really, there's very few luxuries in life that can't be fixed by just a good, solid, good toilet paper. You'll be unhappy when you cheap out with the toilet paper. I'm guaranteeing it. So always spring for the better toilet paper. There is an unbalanced force in this system. You can assume the weight of the toilet paper acts at its center. And there's going to be a tension acting at its edge. These will be unbalanced. They have to be. The toilet paper does accelerate downwards. But be careful. Treat the toilet paper as a disk. That will help. Your answer will not depend on M. You will get a percentage of G, guaranteed as your end product. Show your work, but you have to pick where it rotates. Where's the pivot point here? A lot of people think it's right here, that it pivots about its center. It actually doesn't. It pivots about here. But here's the problem. You don't have the moment of inertia of a disk about its edge. You have the moment of inertia about its center. So you have to do the problem this way. You have to. It's okay. It still works. I promise. Net force, net torque. It'll work just fine. But tomorrow, I would like to know the acceleration when you come to school. All right? The linear acceleration, of course. We're actually going to conduct this lab. You'll all have an opportunity to measure it. You guys who are in the classroom, the best way to measure this is video physics. Does a great job, which is how we're probably going to do it. I'll encourage you guys at home to do the same. But that will mean we need a roll of toilet paper. So if you're feeling, I have many rolls of toilet paper, but maybe not enough for everybody to use because a lot of it was the good stuff. So I came back and took it out of my classroom and there was a run on no, I didn't. I have a whole drawer of it over there. So we have lots of toilet paper here, but if you bring a roll of toilet paper, I won't be sad about it. Might be willing to, consider that point, at the end of the quarter. So either way, I will probably have enough to make it work or I'll steal it from next door. We're going to take some measurements. First thing in class, we're going to unroll some toilet paper. Video physics, though, is how we're going to take our data. All right? I don't know when the bell rings. Now, tomorrow we're on a homeroom schedule, though. We lose an hour of the day for sophomores. So it will impact us tomorrow. I don't know. They're probably doing something in homeroom for seniors. No, they're not. But they might be. They could be. I doubt it. All right. You guys at home have any questions for me? You have two things to do tonight, moment of inertia and acceleration of toilet paper. Please get it done. All right. Bye, guys at home.